Hi everyone, welcome to today's session. In this video, we will be discussing about composition analysis of mixtures. Thank you for joining and let's begin. In this session, we will be analyzing about mole, mole fraction and mass fraction, average molecular weight, what is basis of calculation, and analysis of mixture of liquids and gases, and problems based on analysis of mixture of liquids and gases. First, let us talk about what is mole. Mole is the SI unit for the amount of substance. It is defined as the quantity of a substance that contains 6.022 into 10 raised to the power 23 elementary entities. This number is also known as Avogadro's number. For example, 1 mole of water contains 6.022 into 10 raised to the power 23 molecules of water. Similarly, 1 mole of oxygen gas contains 6.022 into 10 raised to the power 23 oxygen molecules. Usually, the molar mass of a substance is the mass of 1 mole of that substance expressed in grams per mole. Molecular weight is defined as the mass per number of moles. So, from this expression, we can write that number of moles is equal to mass by molecular weight. So, the mathematical expression of mole is mass by molecular weight. That is, small n is equal to small m by capital M. That is mass by molecular weight. Now, let us do some simple problems in mole and mass calculation. So, first problem, find the number of moles in 100 gram of water. So, the given data is mass is 100 gram. And we know that the molecular weight of water is 18 gram per gram mole. And also we know the formula, number of moles is equal to mass by molecular weight. Mass is 100 gram divided by molecular weight is 18 gram per gram mole. So gram gets cancelled and 100 by 18 will give you 5.56 gram mole. So using the formula n is equal to mass by molecular weight, we can determine the number of moles. In second problem, find m in, that is mass in 6 lb mole of oxygen. So in this problem, the number of moles is given as 6 lb mole. And we know the molecular weight of oxygen is 30 lb per lb mole. Using the formula n is equal to m by capital M, we can rewrite the formula as mass is equal to number of moles into molecular weight. Number of moles is 6 and molecular weight is 32. 6 multiplied by 32 will give 192 lb of oxygen. So the mass of the oxygen can be found out by using the formula number of moles of oxygen into molecular weight of oxygen. Let us discuss about mole fraction and mole percentage. Mole fraction is the ratio of number of moles of a component to the total number of moles of all components in the mixture. So mathematically it can be expressed as individual number of moles by total number of moles. Then the mole percentage can be defined as the mole fraction into 100. That is individual number of moles by total number of moles into 100. So let us solve a simple problem regarding mole and mole percentage. In a solution containing 2 moles of ethanol and 3 moles of water, calculate the mole fraction and mole percentage of ethanol and water. So let us frame a table so that it would be easy for us to do the calculations. First, let us write down the components in the given problem. The two components given in the problem is ethanol and water. So the ethanol, the number of moles is 2 and for water it is 3. First let us make the total. 2 plus 3 is equal to 5. Then we know mole fraction is equal to individual mass by total number of moles. So individual mole for ethanol is 2 divided by total moles is 5. So 2 divided by 5 is equal to 0.4. Next for water, the individual is 3 divided by total is 5. Then the mole fraction is 0.6. Always the summation of all the mole fraction will be equal to 1 and the sum of all mole percentage will be equal to 100. Next, mole percentage, we know the formula. It's a multiplication of mole fraction into 100. That is for ethanol, 0.4 into 100, it's 40%. And for water, it's 0.6 into 100, it is 60%. The total is equal to 100%. So the mole fraction is defined as the individual number of moles by total number of moles, and mole percentage is the mole fraction into 100. Similarly, like next look on to the concept of mass fraction, mass percentage and average molecular weight. So mass fraction is the ratio of the mass of a component to the total mass of the mixture. So it is expressed as individual mass by total mass. Similarly, as that of mole percentage, mass percentage is equal to mass fraction into 100. That is individual mass divided by total mass into 100. Then let us talk about what is average molecular weight. Average molecular weight is the ratio of total mass to the total number of moles, and it can be mathematically expressed as average molecular weight is equal to total mass by total number of moles, that is small m by small n. Let us solve a simple problem based on average molecular weight. The statement of the problem is calculate the average molecular weight of air and its composition by weight percentage. Given is 79% of nitrogen and 21% of oxygen by moles. So the problem statement is given in mole percentage. From this we have to calculate what is mass percentage and what is average molecular weight. So similarly, as the previous problem, let us make out a table and list out the components. The two components given in the problem are nitrogen and oxygen. And the number of moles they have given is, that is mole percentage they have given, that can be directly taken as number of moles. So the number of moles of nitrogen is 79 and for oxygen it is 21. How we are calculating, how we are converting 79, directly taking 79% of nitrogen as 79 kilomole is that 79 divided by 100 into 100 will give you 79. Then we should write down the molecular weight of nitrogen and oxygen. The molecular weight of nitrogen is 28 and the molecular weight of oxygen is 32. Then by using the formula mass is equal to number of moles into molecular weight, we can calculate the mass of nitrogen and oxygen. For nitrogen, the number of moles is 79 and the molecular weight is 28. Thus, this 79 into 28 will give you 2212. Similarly, for oxygen, 21 into 32 is 672. Then make the total, that is 2212 plus 672 is 2884. Then easily we can calculate mass fraction and mass percentage. We know mass fraction is individual mass divided by total mass. Individual mass of nitrogen is 2212 divided by total mass is 2884, that is 0.767. Multiplied by 100 will give you the mass percentage 76.7 percentage. Next, for oxygen, the individual mass is 672 divided by total mass is 2884, that is 0.233. Multiplied by 100 will give you the mass percentage of oxygen, that is 23.3 percentage. Here the total mass is 2884 and the total number of moles is 100. Next we have to calculate the average molecular weight. Average molecular weight is calculated by using the formula total mass by total number of moles. Total mass is 2884 and total number of moles is 100. So 2884 divided by 100 will give you 28.84, that is approximately equal to 29 kilogram per kilomole. Next, we are going to discuss about the very important topic in the stoichiometry, that is basis of calculation. The basis of calculation refers to the reference quantity or assumption used to simplify and standardize calculations in chemical engineering and process analysis. It helps in performing mass and energy balances, determining compositions and evaluating system properties. A proper choice of basis frequently simplifies the problem. Usually, it is better to choose either 1 or 100. For liquids and solids, weight analysis is typically used and it is convenient to take 100 kg as the basis. For gases, choosing 1 or 100 moles is often preferable, that is mole percent. First, let us discuss about analysis of mixture of liquids and then go with the analysis of mixture of. The problem statement is a liquefied mixture of N-butane, N-pentane and N-hexane has the following composition in mass percentage. That is, for butane it's 50%, pentane 30%, and hexane 20%. And out of that they are asking us to calculate what is mass fraction, mole fraction of each component, and also the mole percentage of each component, and average molecular weight. So let us list down the components present in the problem: butane, pentane, and heptane. The percentage can be directly written as masses 50, 30, and 20, and the total is equal to 100. And mass fraction can be calculated as individual mass by total mass. Individual mass is 50 and total mass is 100. So 50 by 100 is 0.5. And then for pentane, it's 30. 30 divided by total mass 100 is 0.3. And similarly for hexane, 20 by 100 is 0.2. Then let us write down the molecular weight of all the three. First one is 58. For pentane, it's 72. And for hexane, it is 86. And let us next calculate about the number of moles. The number of moles can be calculated by mass by molecular weight. Mass is 50 divided by its molecular weight is 58. For the second one, mass is 30 divided by its molecular weight is 72. Third one, the mass is 20 divided by its molecular weight is 86, which is given over here with all the values of 0.8621, 0.4161, and 0.2326. And the total of all these three total number of moles is 1.5114. And mole fraction. Mole fraction, we know the formula. Mole fraction is individual moles by total number of moles. So if for the first one, 0.8621 divided by 1.5114, that will give you 0.5703. So multiply by 100 will give us the mole percentage 57.03%. For the second one, 0.4167 divided by its total number of moles is 1.5114, that is 0.2757, and multiplied by 100, the mole fraction will give you the mole percentage 27.57%. For the last one, pentane, 0.2326 divided by total moles is 1.5114, that is 0.540, multiplied by its 100, multiplied by 100 will give you the mole percentage as 54. Now when we make all this total, it will be equal to 100%. Next, let us calculate the average molecular weight. Average molecular weight is total mass by total number of moles. Total mass is 100 and total number of moles is 1.5114. That is equal to 66.16 kg per kilomole. So in this problem, we should write the basis of the problem. So what is the basis of the problem? In what is the data given? It is given as 50 kg, 30 kg, and 20 kg, and total is 100 kg. So then the basis of the problem is 100 kg of mixture. So what is the data given in the problem and what is the total coming out can be written as the basis of the problem. So with this basis only 100 kg of the mixture, we are calculating what is the mass fraction, what is the mole number of moles, mole fraction, mole percentage, and average molecular weight. Next, let us talk about the analysis of mixture of gases. For analysis of mixture of gases, we have to go for an assumption. Assume a gas mixture behaves as an ideal gas when analyzing its properties. For an ideal gas, we know that mole percentage is equal to volume percentage is equal to partial pressure percentage. And for an ideal gas, the density can be calculated by using the formula Pm average by RT, where P is the pressure, M is the average molecular weight, R is the gas constant, and T is the temperature in Kelvin. There are different values of R for the R, but most widely used values in engineering calculations is listed over here. That is, R is equal to 8.314 joule per mole Kelvin, or R is equal to 1.9856 calorie per mole Kelvin. It can be written as 0.08206 liter ATM per mole Kelvin, and also 0.08206 meter cube ATM per kilomole Kelvin. Usually, while calculation, we will use two type of conditions. One is STP, another one is NTP. The STP is represented as standard temperature and pressure, in which the temperature is 0 degrees Celsius and the pressure is 1 atm. So this type of STP calculation is used in scientific calculations, gas laws, thermodynamics, standard states. And next one is NTP, that is normal temperature and pressure. which takes the temperature 20 degrees Celsius and the pressure at 1 atm, which is mostly widely used in engineering, industrial gas measurements, real world gas applications. Let us solve a problem based on the analysis of mixture of gases. The problem statement is a gaseous blend has the following composition by mass, that is CH4 48%, CO2 20%, NH3 12% and N2 20%. They are asking us to determine the following, that is composition by volume percentage and partial pressure percentage, composition by weight percent, average molecular weight, and they are asking us to calculate the density of the mixture at STP and NTP conditions. Atomic mass of all the individual is given as 12, 1, 16 and 14 for carbon, hydrogen, oxygen and nitrogen respectively. Let us solve the problem. First, let us list out what are all the components present in the problem, that is CH4, CO2, NH3 and N2. It is given in mass percentage. So while solving this problem, we have to clearly see in what composition the components are given. Either it's given in mass percentage, mole percentage or volume percentage. In the given problem, the composition is given in mass percentage. So list out the mass percentage 48, 20, 12 and 20, which can be directly taken as mass in terms of kg, that is 48, 20, 12 and 20. And let us write down the molecular weights of the constituents. For CH4 it is 16, CO2 44, NH3 17 and N2 28. Then molecular number of moles can be calculated by using the formula mass by molecular weight. That is 48 by 16 will give you 3. For the second one, 20 divided by 44 is 0.45. And for the third one, it's 12 divided by 17 is 0.705. And the last one, 20 divided by 28 is 0.71. Next, mole percentage. Mole percentage is individual number of moles divided by total number of moles into 100. Individual number of moles is 3 divided by total number of moles is 4.865 into 100 is 61.7. For the second one, 0.45 divided by 4.865 into 100 is 9.3 percentage. Next one, 0.705 divided by 4.865 into 100 is 14.5 percentage. For the last one, nitrogen, 0.71 divided by 4.865 into 100 is 14.6 percentage. So when we assume the gas to be ideal, we know that mole percentage is equal to volume percentage is equal to partial pressure percentage. So the mole percentage takes the value of volume percentage and partial pressure percentage. Next, to calculate the average molecular weight. Average molecular weight is the total mass by total number of moles. Total mass is 100 and total number of moles is 4.865. So 100 by 4.865 is 20.55. So the last one we need to calculate is the density of the gas mixture in kg per meter cube at STP and NTP conditions. We know that at STP pressure is 1 bar and temperature is 273 Kelvin. And also we know the formula Pm by RT. Now pressure is 1 and average molecular weight is 20.55 divided by, since pressure is given in 1 bar, the R value is taken as 0.08206 into 273. So the density is 0.9167 kg per meter cube. At NTP conditions, we know pressure is 1 bar and temperature is 293 Kelvin. So by substituting 1 into average molecular weight is 20.55 divided by 0.08206 into 293 gives 0.855 kg per meter cube. Similar problem in analysis of mixture of gases. A gaseous blend has the following composition by mole percentage. Previous problem we discussed with composition based on mass percentage. This problem we will be discussing based on composition by mole percentage. Propane 34%, butane 30%, methane 28%, nitrogen 8%. And we have to determine the volume percent, partial pressure percent, mass percent, average molecular weight and the density of the mixture at 1 atm and 50 degrees Celsius. Here they have mentioned the pressure and temperature. And individual atomic masses is given to calculate the molecular mass. So let us go for the solution of the problem. First, let us list out the components in the problem. That is butane, methane, propane, butane, methane and nitrogen. Their mass mole percentage is given to be 34, 30, 28 and 8. Here itself we can assume that gas to be ideal. If a gas is to be ideal, then mole percentage is equal to volume percentage is equal to partial pressure percentage. So the mole percentage is equal to volume percentage is equal to partial pressure percentage. The first one is done. The next one is the mole percentage can be directly taken as number of moles, that is 34, 30, 28 and 8. Let us make the total of number of moles, that is 100. So the basis of our problem is 100 kilomole of gas mixture. So with this basis only we are going to calculate mass percentage, average molecular weight and pressure. Next, let us write down the molecular weight to write down the calculate the mass. For the first one, the molecular weight is 44. For the next one, butane, it's 58. For methane, it's 16. And for nitrogen, it's 28. So the mass can be found out by using the formula number of moles into molecular weight. That is 34 into 44 is 1496. For butane, it's 30 into 58, 1740. For methane, 28 into 16 is 448, and for nitrogen, it's 8 into 28, 224. Let us make all the total of 4 to give 3908. Next, we know that mass percentage is individual mass divided by total mass into 100. Individual mass is 1496 divided by 3908 into 100. Next one, 1740 into 3908 into 100, that is 44.52. Third one for methane, 448 divided by 3908 into 100, that is 11.46. For the fourth one, 224 divided by 3908 into 100, that is 5.73. And average molecular weight is total mass by total number of moles. Total mass is 3908 divided by 100 is 39.08. Next, let us calculate the density. Density at pressure 1 atm and 50 degrees Celsius. So the temperature at degrees Celsius has to be converted into Kelvin by adding that with 273. So it will give you 50 plus 273 is 323 Kelvin. Density calculation is Pm by RT, where P is 1 and the average molecular weight is 39.08 divided by 0.08206 into 323, and it gives you 1.475 kg per meter cube. So the density value is 1.475 kg per meter cube. So in this session we have discussed about mole, mole fraction, mass fraction, average molecular weight and analysis of mixture of liquids and gases. Thank you.